My name is SM Mojahidul Hassan, representing my team, Team Extractors. My teammates are Mahmudul Hassan and Tanvir Hossain. We all are doing our PhD at the University of Kansas under the supervision of Dr. Tamjidul Haq. We are participating as a red team here in the logic locking competition of Hello CTF 2022. Let's start with some highlight of our work. So, we are introducing our attacking framework, key extracting assertion through transformation of netlist, in short, KEATON, which is developed by my colleague Mahmudul and our supervisor Dr. Haq. The paper written on this attack is recently accepted in the AsianHOST 2022 and it is nominated for the Best Paper Award. We could retrieve full or partial key bits for 2 designs out of 3 given log designs using our attack in combinational logic locking track and found the logic cone for design 3 by analyzing it structurally. Alright, now we know that some fundamental security issues involved with hardware IPs are IP piracy, overproduction, and reverse engineering. These kinds of hardware level threats can be introduced by any unreliable parties from the IC manufacturing supply chain, such as untrusted foundry, testing facility, or even end users. One of the proven solutions to these threats on hardware IP is logic locking techniques. Logic locking can either be combinational or sequential. So, as a red team here in Hello CTF 2022 competition, our objective is to find vulnerabilities of existing logic locking techniques, especially techniques that are used to obfuscate the given designs by the Hello CTF blue team. To do that, we have employed KEATON definitely. It is an oracle or functional input-output sequence guided attack, and it can extract keys from both combinational or sequential logic locking techniques. Look at the threat model, which are the assumptions we made for our attacking framework. First, we considered that the designers and the design houses in the IC supply chain is a trusted entity. Second, the adversary can be anyone from the IC fabrication facility, packaging facility, testing facility, or an end user. Third, we are assuming that the attacker has access to the log netlist and a functional IC which is given as an oracle in this competition for us. Also, the attacker can utilize the input and key input ports names for log designs while attacking with KEATON framework. Okay, so now I'm gonna present the overview of our attacking framework KEATON with a little more technical details. At first, we need to know the function of an assertion-based formal verification tool. Well, such formal verification tools can return the specific input condition for which a given property of a circuit is true. We utilized this powerful feature of the formal verification tool in our attacking framework KEATON to verify certain oracle conditions. Now, starting with the main framework, first of all, we modify the log design with a set of oracle, and the oracle is used to create an oracle verifying finite state machine. We call it OVFSM. Also, a counter is implemented for stopping any transition in key sequence, while the formal verification tool tries to solve for the OVFSM. After that, it writes an assertion for formal verification tool to query the key for which the selected input-output pairs are valid. For a given oracle, the query outputs a fixed key sequence if it satisfies the IO condition. Otherwise, it returns to a black hole state. Once we retrieve key sequence for one set of oracle, we perform the analysis for different sets of oracle sequences, and all the query outputs are compared, and finally, a key bit sequence has been observed by a probabilistic approach. Finally, the found key bits are applied directly to the log design with the previous inputs. Then the produced output is compared with the oracle output to verify the effectiveness of the key sequence. Now let's take a look at the locking technique that we are dealing with. All the given designs in the combinational logic locking track are locked with strict functionality logic locking technique, in short SFLL. SFLL are primarily proposed as two types, and those are SFLL HD and SFLL Flex. The basic idea behind SFLL is to strip some functionality of the original circuit for a set of protected input patterns. By doing that, it produces a functionality stripped circuit which conceals the original output for the given input patterns. For SFLL HD, the protected input patterns are selected based on the Hamming distance from the correct key bits. The restoration for SFLL HD uses a separate block of circuit called restore unit and compares the protected input pattern and the correct key bits to match with a predefined Hamming distance. Once the correct key bits are supplied, it restores the original output by flipping the output of FSC circuit. Unlike SFLL HD, SFLL Flex allows user to specify the protected input patterns. In this technique, the protected input patterns are stored inside the restore unit in a form of input cubes. To restore the original functionality of the circuit, the input cubes are used as a secret key and loaded onto the chip. Well, now before applying our KEATON attacking framework, we first did a structural analysis on a given combinational design to find the critical inputs that produces the protected input patterns. Since all the given designs have key inputs, we presumed them to be logged with SFLL HD. At first, we targeted the restore unit, which should get all the key inputs as input, and found the protected outputs. Then we traced back to find the possible critical inputs. Once we get the probable set of critical inputs, we then tried to find distinguished input patterns for them to get effective oracle for our KEATON framework. We performed this operation for multiple iterations and used a majority voting technique to finalize the keys that can uncover most of the functionality of the given log designs. Now, let's talk about the implementation of KEATON on the given designs a little bit. At first, when we collected the deeps, we fed them to the functional chip given as an executable file with each design and produced effective I/O sequence pairs. Second, we created the OVFSM using those I/O sequences and insert them into the top module along with the log design. Next, we inserted the counter blocks to stop any positive or negative transition in the found key sequences by the Jasper Gold. Once the Jasper Gold satisfies all the OVFSM and reaches at the end, we get the key sequence for the given oracle. The table shows the recovered keys for design 1 and design 2. We have also tried our attack on design 3. However, for the given oracle sequence, the formal verification tool could retrieve most of the functionality with all the key bits to be 1. It happened because it has only one output node. The oracle for this attack contained only 400 to 500 input-output patterns. The key bits are verified by simulating them for multiple set of random inputs up to 1 lakh sequences. In 3, however, we figured out that 493 inputs out of 522 inputs are not actually in use in the design. Thus, we excluded those inputs and mapped the circuit structurally. We found that the key bits are splitted and a subset of them are fed to the FSC as well, in addition to the restoration circuits. An overall understanding of design 3 protected logic cone has been depicted in figure 8. Since our attacking framework uses industry standard tools to perform this attack, it is highly accessible to adversarial entities since no complicated algorithm needs to be harnessed. Real industrial IPs are mostly power, performance, and area focused and cannot afford to have so many key bits or obfuscation logics to log the designs. Hence, they can be a potential target of our attacking framework. We have come to this point by mostly using the inherent capabilities of our attacks, but with more pre-processed designs, it is possible to retrieve all the key bits.